Hello everyone, my name is Jake Sekosky,
My name is Martin Heraldez.
and this is our lab report on detectors. This is lab 11 of OPTI380. So the main goal for this lab is going to be analyzing the differences between a pin photodiode, photoconductor, and avalanche photodiode, with the ultimate goal being how can we apply these optical devices to different situations. We're going to be putting a heavier emphasis on the pin photodiode, which represents the p-type, n-type, and intrinsic levels of a semiconductor, and see how it affects things like voltage, current, and fall time. Then the second part will be about an infrared setup and trying to capture images based on that setup.
So our objective for part A was to compare the behavior of a PIN photodiode, an avalanche photodiode, and a photoconductor by examining the responsivity, noise performance, and temporal response. The first thing we did was place the APD 10 millimeters from our LED in our PIN photodiode 100 millimeters from the LED, and then we drove the LED at a low amplitude to examine the sensitivity of both detectors. We then replaced the APD with our second photodiode and connected our photodiode to the multimeter to record the voltage of the open circuit as well as the current of the short circuit while making plots comparing both of these values to optical power. For the next part, we replaced the PIN photodiode with the photoconductor, from which we were able to power the circuit and measure the voltage across the series resistor while sweeping the LED brightness. This gave us the photoconductor's voltage response to optical power. Then we were able to move to the temporal response test, where we connected the PIN photodiode directly to the oscilloscope without the resistor and illuminated it with the strobe light, and then we added the resistor before measuring and comparing the fall times. So the top left picture captures the APD and the PIN photodiode signals under the same LED drive, where the APD is more accurate at lower drives as the waveform is still visible. And for the rest of the plots on the right, we can see that there is a linear increasing trend for all four, which adheres to the expected values from the given charts. For the next slide, we weren't able to get the exact measurements, but we were able to approximate the left fall time as 4 milliseconds and the right fall time is about 1 millisecond, which shows that adding a resistor decreases the fall time. So for part B, we sought to demonstrate how a CMOS camera responds to both visible and infrared light. We began by setting up a camera on the rail and capturing images under white light illumination, and then inserting an IR blocking filter. We then repeated this experiment with an IR LED illuminating our target. As for our results for part B, we could see that nothing really changed upon inserting the IR filter under white light illumination, since different wavelengths of light made it through the filter. However, when the illumination source was IR light, most of the light was blocked.
In real-life scenarios, you should use an avalanche photodetector to detect weak signals, a photoconductor when you want resistance to change, and a photodiode when you want to use something with infrared light. Without a resistor, the fall time of the setup greatly increased with an increase of 1 to 4, which is 300%. And the infrared filter completely changed the infrared setup. Go figure.